Hello everyone. Hope you are doing very well. So today we are going to do the NEET PYQs, NEET previous year questions that has been there in the previous NEET examinations, and our chapter is D and F block elements. So let's begin today's topic, that is NCERT chapter 4 D and F block elements, NEET PYQs. This is disclaimer. So let's begin with our first question, which is a NEET PYQ and covering the NCERT section 4.3. The question is that identify the incorrect statement. So you have to identify the incorrect statement among the given statement given in the options. The options are: the transition metals and their compounds are known for their catalytic activity due to their ability to adopt multiple oxidation states and to form complexes. So, this is the first statement. The second statement: interstitial compounds are those that are formed when small atoms like hydrogen, carbon, or nitrogen are trapped inside the crystal lattices of metals. The third statement: the oxidation states of chromium in CrO4 negative and Cr2O7 negative are not the same. And the fourth statement is that chromium 2 positive in the configuration D4 is a stronger reducing agent than iron 2 positive in the D6 configuration in water. So you have to identify the statement that is incorrect, not correct. So try to solve this question, like try to go to the statements one by one and the properties the statements are talking about. Try to remember that from the chapter, and then you can answer this question after the given time. Let's see. So for this question, the correct answer is C statement. That means the incorrect statement is C statement, which is saying that the oxidation states of chromium in CrO4 negative and Cr2O7 negative are not the same. Let's analyze the each statement given in the question to identify the incorrect one. Let's analyze the first statement, that is A statement first. So, which says that the transition metals and their compounds are known for their catalytic activity due to their ability to adopt multiple oxidation states and to form the complexes. Okay, so you have to identify the statement and you have to explain the statement to identify either it is the correct one or incorrect one. So it is a correct statement. Let's see how. So explanation includes the vacant d orbital. So you know that the transition metals have vacant d orbitals, empty d orbitals present in them, and due to the presence of vacant d orbitals, they exhibit variable oxidation states, right? So because they have vacant d orbitals, they can exhibit variable oxidation states by the either gaining or the losing of electrons present in the d orbital of the transition metals, right? Form complexes. Now, via showing the variable oxidation states, they form complexes by stabilizing the intermediates without even consuming. Okay, so what they did, they basically have the transition metals have vacant d orbitals in them, in which the electrons can fill up, or the electrons can even be donated from the d orbital to make or to exhibit the variable oxidation states, right, which is shown by transition metals. Now, due to this property of showing of having different oxidation states, they form complexes by stabilizing the intermediates formed in the reaction without consuming. That means they are going to act as a catalyst by forming the complexes and stabilizing the unstable intermediates. Okay, without consuming, without acting as a catalyst, because this is the property of the catalyst, that catalyst participate in the reaction, and without consuming into it, it increase the rate of the reaction, and due to which the transition elements are also, like transition metals also act like that, because they show different, or they are existing in different oxidation states, so they are able to form complexes, and they stabilizes the intermediates without consuming in the reaction. That means after acting as an catalyst. So what is the conclusion? That this statement is the correct statement. The statement which says that the transition metals and their compounds are known for their catalytic activity. Catalytic activity means they are going to act as catalyst in the reaction without consuming in the reaction. Why? Due to their ability to show, or to adopt the multiple oxidation states by either gaining or losing of electrons, and to form the complexes by stabilizing the intermediates formed in the reaction. Okay, so this is statement given. Statement A is the correct statement. Now let's see the statement B, which says that interstitial compounds are those that are formed when the small atoms like hydrogen, carbon, or nitrogen are trapped inside the crystal lattices of the metals. So this is the statement B. Uh, Statement B is talking about the interstitial compounds, that the interstitial, this type of compounds formed when the small atoms like hydrogen, carbon, or nitrogen gets trapped inside the metal's crystal lattices. Okay, so this is a correct statement. Let's see the explanation. The formation of interstitial compounds. So how the interstitial compounds form, that you have to identify, right? That you have to talk about. So interstitial compounds formation include when the small non-metal atoms like hydrogen, carbon, boron, or nitrogen, small atoms, that means they are having small atomic number, and as so the atomic size, right? So the small non-metal atoms like hydrogen or nitrogen, when they fill in the interstitial voids, in the interstitial spaces, uh, like made between the atoms, or two different atoms of same element, right, in the transition metal crystal lattices. So in the transition metal crystal lattices, they can be arranged in different lattices, BCC, CPP, right? So in those crystal lattices of transition metals, the atoms of the transition metal are arranged in some manner, right, in 3D space, and between the two atoms there will be a space, or between the three atoms there will be a space created, which are known as void. And in those void, or interstitial voids, small non-metal atoms, which is having a smaller size, which is comparable to the void created, so they are trapped, or they are fitted in those voids in the transition metal crystal lattices, and that's how the interstitial compound formation happens. Okay, that's why we are calling these compounds as interstitial compounds, when at the interstitial sites or interstitial voids the smaller non-metal atoms gets trapped in the metal crystal lattice. So the conclusion is that the statement B given is correct statement, that interstitial compounds are those that are formed when the small atoms like hydrogen, carbon, nitrogen trapped inside crystal lattice of metal. So this is the correct statement. Now let's see the third statement, that is C statement. So the oxidation states of chromium in CrO4 2 negative and Cr2O7 2 negative are not the same. So this statement is saying that if you see the oxidation state of chromium in these two ionic compounds, they are not same. This is what statement he is saying, and this statement is basically incorrect. Let's see the explanation. So let's first talk about the first ionic compound, chromium O42 negative, which is a chromate ion. Okay, so for this chromate ion, we are talking about the oxidation state of chromium in this ion. So let the oxidation state, to find out the oxidation state of chromium, let's suppose its oxidation state is X in this ionic compound. So we know that oxygen typically has an oxidation state of -2, right? So here oxygen will exhibit this oxidation state of -2, which it generally have. Okay, so we just try to balance the oxidation states of chromium and oxygen with the charge of the compound. So X, which is, we supposed the oxidation state of chromium, so X plus 4 times the oxidation state of oxygen, which is -2. So X plus 4 times -2 is equals to the whole charge which is present on the whole ionic compound. So that is -2. So X plus 4 times -2 is equals to -2. 4 times -2 is -8. This implies X times X minus 8 is equals to -2. Now this -8 goes here at the right hand side and form X equals to -2 plus 8, and then we do the subtraction. 8 minus 2 will be 6. So X is coming out as plus 6. That means X, we have considered the oxidation state of chromium. So oxidation state of chromium is plus 6 in this ionic compound CrO42 negative. Okay. So we have calculated the oxidation state in one ionic compound. Now let's calculate the oxidation state in the another one to determine whether our C statement is correct or not. Now for the diachromate ion, which is Cr2O72 negative as given in the question, we apply the similar steps. So we supposed the oxidation state of chromium in this ionic compound as Y for identification of the chromium oxidation state. Now we know that oxygen will typically has an oxidation state of -2. So here also oxygen will exhibit the -2 oxidation state. Now we balance the each atom oxidation state with the whole charge that is present on this ionic compound. So 2Y, because 2 chromium, so 2Y plus 7 times -2. 7 atoms of oxygen is present. So 7 times -2 is equals to the whole charge present on the whole ion. So equals to -2. Okay, so 2Y plus 7 times -2 equals to -2. 7 times -2 is -14. So this implies 2Y minus 14 is equals to -2. Right? Now we solve it. So 2Y will become -2 plus 14. This -14 will go here in the right hand side. This implies 2Y is equals to 14 minus 2 is 12. So 2Y equals to 12. Now you divide 12 by 2 and Y will become equals to 6 because 2 times 6 is 12. So the oxidation state of chromium in this diachromate ion is coming out as plus 6. Conclusion that the oxidation states of chromium in both this chromate ion and diachromate ion are plus 6. Okay, so we just have calculated that the oxidation state of chromium in these two ions are same, that is plus 6. Therefore, the statement that the oxidation state in those ions are not same is incorrect. Okay, so the statement C is going to be our incorrect statement. Now let's also see the D statement. So D statement is that chromium 2 positive having D4 configuration is a stronger reducing agent than the Fe2 positive having D6 configuration and in the water. So we are talking that chromium 2 positive is stronger reducing agent than iron 2 positive in the water. That you have to tell. So this statement is correct statement. Let's see how. Explanation includes that reducing agent. First of all, we have to identify about the reducing agent here. And reducing agent, if you know the definition, reducing agent is a species that is going to lose its electron by gaining or by getting oxidized itself. Okay, so reducing agent means it is going to reduce others and gets oxidized itself. So this is a species that is going to lose electrons and gets oxidized, and its strength, the reducing agent strength, is related to its tendency to lose electron. How efficiently it can lose electron, the strength of reducing agent is dependent on this factor. So we are talking about the chromium 2 positive, right? So chromium 2 positive when convert to chromium 3 positive, that means oxidation is happening. Okay, that's what a reducing agent do. It's oxidize itself, get reduce others. So chromium 2 positive to chromium 3 positive, we have to talk about. Chromium 2 positive already given has a D4 configuration. Meanwhile, it loses one electron to become chromium 3 positive, right? If you want to obtain the chromium 3 positive from chromium 2 positive, you have to lose one electron from the D4 electronic configuration, and that means our chromium 3 positive is going to attain a D3 configuration, right? So the configuration is changing from D4 to D3. Now in an aqueous environment in the water, the D3 is stable due to half filled T2G3 configuration. Okay, so in the aqueous medium, in the aqueous environment, this D3 configuration is going to be the stable one. Why? But because it is going to attain the half filled T2G3 configuration. So T2G3 is the configuration that is going to attain by the d electrons when the dd transition happens between the two different energy levels, Eg and the T2G. Eg is the upper one, T2G is the lower one, and T2G having three energy like spaces provided to for the filling of the d electrons after the dd transitions. Three spaces are provided, that means in total 6 electrons can be filled in it, and d3 means 3 electrons is going to filled in the T2G 3 energy levels or 3 energy spaces. Each space will going to have one unpaired electron, right? That means T2G3 configuration is going to be attained by the D3 configuration, and it is a half filled T2G3 stable configuration, right? Similar like D5 configuration. D5 is a half filled stable configuration. Similarly here T2G3 is a half filled stable configuration after the DD transition of D3 configuration for chromium 3 positive. So this strong tendency to achieve the stable D3 configuration from the D4 configuration of chromium 2 positive makes the chromium 2 positive a good reducing agent. Okay, that's why chromium 2 positive wants to get stabilized by losing its one electron, converting to chromium 3 positive and attaining a D3 or T2G3 half filled configuration. Okay, so chromium in the 2 positive have this strong tendency to convert to the chromium 3 positive. That means it is going to like act as a good reducing agent. By losing its electron, it gets oxidized and gets stable, attaining half filled T2G3 configuration. So chromium 2 positive is a good reducing agent. If you talk about the iron 2 positive, so iron 2 positive to iron 3 positive. Here, the iron 2 positive has a D6 electronic configuration. Okay, so iron 2 positive has a D6 electronic configuration. It loses one of its electrons to become Fe3 positive to act as a reducing agent by getting oxidized itself and reducing others, right? So Fe2 positive is going to lose its one electron to become Fe3 positive, and it is going to attain a D5 configuration after it. Now, in an aqueous environment, that means a high spin octahedral environment where the high spin octahedral member or complex is present, the D5 also corresponds to a stable half filled T2G3 and EG2 configuration, right? So, as I said that after DD transition, the electrons are going to fill from the d orbital to T2G and EG orbitals. EG is the upper one, T2G is the lower one. T2G have three different energy bars or three different energy spaces for providing for the 3 unpaired and 6 totally paired electrons, and the EG has 2 energy spaces provided for 2 unpaired and 4 totally paired electrons filling into it, right? So in the aqueous environment where we are taking the high spin octahedral, a D5 configuration corresponding to a stable half filled T2G3 and EG2 configuration. Okay, Okay, so the electrons are going to fill 3 electrons in the D2G3, making it half stable configuration, and 2 electrons are going to fill in the EG level, making it a half filled stable configuration. Now, if you compare their reduction potentials, so the E naught, the standard reduction potential for the chromium 3 positive to chromium 2 positive is negative of 0.41 volt. Meanwhile, the E naught of iron 3 positive to iron Fe2 positive, the E naught is positive 0.77 volt. Okay, so more negative or less positive standard electrode potential indicates a stronger reducing agent for lower oxidation state species. Okay, more negative, that means if you have a more negative or a less positive value of the standard electrode potential E naught, this is going to indicate that a stronger reducing agent for the lower oxidation state species are present. Okay, now if you compare between these two standard reduction potential values for chromium and iron, the standard reduction potential value of chromium 3 positive to chromium 2 positive is much more negative than the E naught of iron 3 positive to iron 2 positive, right? So chromium 2 positive has a greater tendency to get oxidized to chromium 3 positive if you compare to iron 2 positive getting oxidized to the iron 3 positive. Okay, so chromium 2 positive has a greater tendency to oxidize to chromium 3 positive and attaining a D3 or T2G3 half filled stable configuration, comparing to the iron 2 positive getting oxidized to iron 3 positive and attaining the T2G3 EG2 half filled stable configuration. Okay, so because from the configuration we were not clear, so we are comparing it their reduction potentials also, from which we have concluded that more negative standard electrode potential indicates stronger reducing agent for the lower oxidation states. And since the E naught value is more negative for the chromium than the iron one, so that means the chromium 2 positive has greater tendency to oxidize to the chromium 3 positive compared to the iron 2 positive oxidized to the iron 3 positive. Okay. Thus, we can say that chromium 2 positive is a stronger reducing agent than the iron 2 positive. So, from here, we can say that chromium 2 positive, by comparing their electrode potentials, that chromium 2 positive is going to act as a stronger reducing agent. That means going to reduce others and getting oxidized itself, than the iron 2 positive and comparatively. So, the conclusion is that the statement is correct, which is saying that the chromium is having or is going to act as a stronger reducing agent than the iron 2 positive. Okay, this statement is also correct. So, final conclusion includes that based on the analysis of every option, the statement C given is the incorrect one. So, we have to identify the incorrect statement in the question. So, the correct answer is going to be our option C, the statement C. Okay, let's move to our next question. This is a NEET PYQ and this is covering the NCRT section 4.3.9. Question is that magnetic moment, which is 2.84 Bohr magneton, is given by. So we have given the magnitude of a magnetic moment 2.84 Bohr magneton. You have to tell which element is going to give this value of magnetic moment. The atomic numbers for nickel, titanium, chromium and cobalt are given as 28, 22, 24 and 27 respectively. So the options include titanium 3 positive, chromium 2 positive, cobalt 2 positive or nickel 2 positive. You have given some time, try to solve this, try to go on the concept of the magnetic moment we have studied and then try to solve this. After this time we will going to see the correct answer. Let's see. For this question, the correct answer is option D. That is nickel 2 positive. So the magnetic moment, we are talking about the magnetic moment in the question. So the magnetic moment is given by mu is equals to under root n plus 2 Bohr magnet. Here, the n is representing the number of unpaired electrons present in the element. Let's calculate the magnetic moment for each option. So for the first one, that is titanium 3 positive, titanium has a like atomic number of 22. The Z of the titanium is 22. So its electronic configuration will be argon 3d24s2. Okay, argon for the like noble gas configuration of argon, and the remaining configuration for outermost orbital, that is 3d2 and 4s2. Now for titanium 3 positive, the electronic configuration will be argon 3d1, because 3 positive means 3 electrons it is going to lose, 2 from the 4s and 1 from the 3d. So only remaining configuration is argon 3d1, where n, that is number of unpaired electron, is equals to 1. So mu will become under root n plus 2 Bohr magneton. You put n equals to 1 here. So mu will become 1 plus 2 times 1, right? 1 plus 2 is 3, 3 times 1 is 3. So this is going to be under root 3. Mu is equals to under root 3 Bohr magneton, or you can write it as 1.73 Bohr magneton. Okay. The magnetic moment given in the question is 2.84 Bohr magneton. So this is not matching with the titanium 3 positive calculated magnetic moment. So this is not going to be the answer, right? Let's solve for next option. So for our next option, that is chromium 2 positive, the atomic number is going to be 24. 24 means the electronic configuration for chromium is going to be argon 3d5 4s1. Argon for argon noble gas configuration, and rest is 3d5 4s1. Okay. Now for the electronic configuration of chromium 2 positive. 2 positive charge means it has loosened its 2 number of electrons. 2 number of electrons from the outermost shell. So one electron will remove from 4s1 and 1 electron will remove from 3d5. So the remaining electronic configuration for chromium 2 positive will be argon 3d4. 3d4 means the unpaired electrons present is going to be 4 in total. So n is equals to 4. Now we put the value of magnetic moment, or the formula of magnetic moment given by mu is equals to under root n plus 2 Bohr magneton, and we put here in this formula n value as equals to 4. So mu will become 4 times 4 plus 2. 4 plus 2 is 6. 6 times 4 is 24. So mu is equals to under root 24 Bohr magneton, or also it can be written as equals to 4.89 Bohr magneton. Okay, so you know under root 25 is 5. So under root 24 is like 4 point something. So here under root 24 is 4.89 Bohr magnet. Now this magnetic moment value is also not matching with the given magnetic moment value in the question. So this is also not going to our correct answer. Let's analyze our C option. That is cobalt 2 positive, and its atomic number is going to be 27. The electronic configuration involves argon 3d7 4s2. Similarly, the electronic configuration for cobalt 2 positive. 2 positive means you have released the 2 number of electrons from it from 4s2. The remaining configuration for cobalt 2 positive is argon 3d7. And in the 3d7 configuration, if you arrange in the orbital, like if you draw the diagram for the 3d electron filling, you got 3 number of electrons as the unpaired electrons. Okay. So mu will be, the magnetic moment will be under root n plus 2 Bohr magneton. So you put n equals to 3. So it will become 3 times 3 plus 2. 3 plus 2 is 5. 5 times 3 is 15. So mu will be under root 15 Bohr magneton, which you can also write it as 3.87 Bohr magneton. So this value of magnetic moment for cobalt 2 positive is also not matching with the magnetic moment given value in the question. So this is also not going to be our correct answer. Now let's analyze the D option. That is nickel 2 positive having the atomic number 28. Similar step we are going to perform. Electronic configuration is argon 3d8 4s2 for the nickel. Now electronic configuration for the nickel 2 positive, that means 2 electrons has been removed. So that 2 electrons will go from this 4s2. Okay. So the remaining configuration will be argon 3d8. If you observe the 3d8 configuration, d8 means only 2 number of unpaired electron is going to be present. Okay. So mu is equals to under root n plus 2 Bohr magnet n. We put the n value equals to 2. So it will become 2 times 2 plus 2 under root. 2 plus 2 is 4. 4 times 2 is 8. So mu is equals to under root 8 Bohr magnet n, which you can also write it as 2.84 Bohr magnet n. Hence, this value of magnetic moment we just calculated for nickel 2 positive is matching with the given magnetic moment. So nickel 2 positive gives the magnetic moment of 2.84 Bohr magnet, which is already given in our question. So that's why this D option is going to be our correct answer. That is nickel 2 positive. Okay, so this given magnetic moment in the question is associated with the nickel 2 positive ion. Let's move to our next question. So this is a NEET PYQ and this is covering the NCRT section 4.3.2. Question is that reason of lengthenoid contraction is. So you have to tell the reason behind the lengthenoid contraction occurs. Options are negligible screening effect of f orbitals, increasing nuclear charge, decreasing nuclear charge, or decreasing the screening effect. So you have given some time to solve this question. After that, we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option A, that is negligible screening of the f orbitals. So you have to tell the reason of lengthenoid contraction and the answer is the negligible screening effect of f orbitals. Now across the lengthenoid series, okay, so we have covered the lengthenoid and the actinoid series, remember, in the F block in the periodic table. So across the lengthenoid series, if you go from lanthanum to lutetium, from La to Lu, the 4f electrons which are added. So the added electron from the lanthanum to lutetium in the lanthanoid series enters the 4f subshell. Okay, so the added electrons enters the 4f subshell, due to which the poor 4f shielding will going to be there. So 4f orbital, because the electrons which are adding from lanthanum to lutetium in the lanthanoid series is adding in the 4f orbitals. So 4f orbitals, because they are diffuse and they are going to provide the poor shielding of outer electrons, that is 5s, 5p and 6s from the increasing nuclear charge. Okay, poor shielding means that outer electrons are having poor shielding from the increasing nuclear charge with every electron adding into the 4f subshell. This leads to a significant increase in the effective nuclear charge on the outer electrons. So due to the poor shielding of the 4f orbitals, the outer electrons in the 5s, 5p or 6s orbitals, they are going to affect by the increasing effective nuclear charge. Okay, so they are going to pull towards the nucleus because the 4f orbital is poor in shielding those outer electrons, and due to which the increasing effective nuclear charge is going to significantly affect the outer electrons. Due to this, electrons pulled closer. So, outer electrons, due to the poor shielding, are pulled closer to the nucleus after affecting by the nuclear charge, or this attraction between the outer electrons and the nucleus are increasing, due to which the outer electrons are pulled closer to the nucleus more. Now, this results in a gradual decrease in the atomic and the ionic radii across the lengthenoid series. And due to this whole region, that the electrons are filling in the 4f orbital, and it is providing poor shielding to the outer electrons, due to which the outer electrons are pulled more closer towards the nucleus due to the increasing nucleus or increasing effective nuclear charge. This is going to affect the size of the atomic or ionic radii. That means that ionic and the atomic radii are going to gradually decrease, and this decrease across the lengthenoid series is known as lengthenoid contraction. Okay, so this is the reason behind the lengthenoid contraction which you observe in the lengthenoid series from lanthanum to lutetium due to the poor shielding of the 4f orbitals. So the correct reason of lengthenoid contraction you have to tell, which is our option A, that is negligible screening effect of the f orbitals. Okay. Okay, let's move to our next question. So this is a NEET PYQ and this is covering the NCRT section 4.3. The question is that which one of the following does not correctly represent the correct order of property that is indicating against it. So you have to tell from the given options that which option is not correctly represent the correct order of the elements for the property which are indicating against this. Okay, so options are highest options. In the first option, we have first given the order for increasing number of oxidation state, which is highest for manganese, then for chromium, then for vanadium, and then for titanium. Second option is given the increasing magnetic moment order, highest for manganese 3 positive, then chromium 3 positive, then vanadium 3 positive, and then titanium 3 positive. Or the third option, given increasing melting points order, highest for manganese, then for chromium, then for vanadium, and then for titanium. And then the D option, giving the increasing second ionization enthalpy order, highest for chromium, then for manganese, then for vanadium, and then for titanium. So you have to tell that which order between the or among the elements which is given for the property indicated against it is correctly or does not correctly represent. Okay, so I have to identify the incorrect order. Okay, so you have given some time. Try to solve this question. Try to remember the properties that we have seen or that we have been observed, studied about the this series, 3D series in the DNF block elements, of which these elements are included: titanium, vanadium, chromium, and manganese. And you have to identify that which is mismatching, like order and the given property which is mismatching, like for which property the order is not given the correctly, that you have to identify. So you have given some time. Try to solve this question. After this, we will see the correct answer. Let's see. So for this given question, you have the correct answer as option C, that is for the increasing melting point order given, highest for manganese, then for chromium, then vanadium, and then titanium. Let's see. So first, let's examine the first option, giving the order of increasing number of oxidation state property. among the 3D elements, highest for manganese, then chromium, then vanadium, then titanium. So increasing unpaired d electrons, as you know, when you move from titanium to the manganese in the 3D series, it is going to show more unpaired d electron after the successive electron filling, like in the 3D elements, right? So from the titanium to the manganese, you will see that there is a more unpaired d electrons is going to occur. So there is increasing unpaired d electrons from the titanium to manganese in the 3D series. Small 3D 4s energy gap. Now between the 3D and the 4s orbital, the energy gap is small enough to allow the both 3D and the 4s electrons to participate in the bonding with another elements, right? What this is going to be give the result? It leads to give us multiple oxidation states, right? Because the unpaired electron or unpaired d electron are increasing, and due to the smaller 3D and 4s energy gap, the 3D and the 4s, both the electrons are going to be involved in the bonding, right? This is going to lead uh, to show the multiple oxidation states by these elements. And titanium has a maximum of 4, vanadium has 5, and chromium has 6. And manganese has the 7, the maximum number of valence electrons in these series. Now, if you talk about the 3D series, manganese has 7 um, valence electrons, which is maximum number of valence electron in the series. Titanium has maximum 4, vanadium has 5, and chromium has 6 valence electrons. Manganese shows widest range of oxidation states because as the valence electron will increase from 4 to 5 to 6 to 7 from titanium to manganese, the range of the oxidation state shown by these elements will also going to increase in the similar manner, right? So as the manganese has maximum number of valence electron, manganese is going to show widest range of oxidation states from +2 up to +7. Okay, for example, you can observe the manganese in +7 in the KMnO4. Okay, so you can see that this order which is given for the increasing number of oxidation states. So manganese having the highest oxidation state, then chromium, then vanadium, then titanium, because this is the order which is following for their valence electrons and the oxidation state range shown by them also. Okay. Now, if we observe for the B, that is the second uh, order which is given for the increasing magnetic moment, in which the increasing magnetic moment highest is for manganese 3 positive, then chromium 3 positive, then vanadium 3 positive, and then titanium 3 positive. Okay, so if you talk about the magnetic moment or spin only magnetic moment, it is calculated as mu is given by under root n plus 2. Here the n is representing the number of unpaired electrons present in the element. So for titanium 3 positive, the electronic configuration is argon 3d1. Okay. Here the n value is equals to 1. So magnetic moment will be under root 1, 1 plus 2. Okay. 1 plus 2 is 3. 3 times 1 is 3. So it is going to be equals to under root 3. That is equivalent to 1.73 Bohr magneton. Okay. In the similar ways, you will find the magnetic moment for each element given in the order, and then you have to compare to see the increasing order of magnetic moment. Now for vanadium 3 positive, the electronic configuration is going to be argon 3d2 with n value is equals to 2. d2 will give the unpaired electron as 2. Okay, so n value will be 2. So magnetic moment will be under root 2 times 2 plus 2. 2 plus 2 is 4. 4 times 2 is 8. So it is equals to under root 8. Okay, and under root 8 is going to be equivalent to 2.83 Bohr magneton. For chromium 3 positive, electronic configuration is argon 3d3. 3d3. d3 means n is going to be equals to 3. That means unpaired electrons is going to be equals to 3. So magnetic moment will be under root 3 times 3 plus 2. 3 plus 2 is 5. 5 times 3 is 15. So it is equals to under root 15. or it is equals to 3.87 Bohr magneton. Similarly, we find out for manganese 3 positive. For manganese 3 positive, electronic configuration is argon 3d4 having n value, that is unpaired electron value, equals to 4. So, magnetic moment is going to be 4 times 4 plus 2. 4 plus 2 is 6. 6 times 4 is 24. So, it is under root 24, which is equals to 4.90 Bohr magneton. Okay. So, if you observe now that the highest value for magnetic moment is for manganese 3 positive, then chromium 3 positive, then vanadium 3 positive, and then titanium 3 positive. So, this order given is the correct order for the increasing magnetic moment, right? Therefore, the given order is the correct order. Now, let's see for the C option, that is given the order of increasing melting points. Highest for manganese, then for chromium, then for vanadium, and then for titanium. So, the chromium is having the higher melting point, then vanadium, and then titanium. This order is correct because melting point increases due to the more presence of unpaired d electrons in the outermost orbital of these transition elements, which is going to strengthening the metallic bonds formed by these elements. Okay, so due to the stronger metallic bond, the melting point is going to increase from the titanium to chromium. Manganese is going to show the anomaly behavior. Why? Because it is going to show the lower melting point value. Why? Because it is having a stable D5 configuration, 3D5 configuration. And due to the stable configuration, the manganese is not going to participate in the metallic bonding, due to which due to the stable D5 configuration, the metallic bonding is going to decrease for the manganese, and due to which the melting point for this is going to be lower. Decreasing melting point, that means there will be lower melting point. It can melt easily. So, because the manganese is showing the anomaly behavior, it is going to have a lowest melting point in the given elements, titanium, vanadium, chromium, and manganese. Okay, because it is showing the less metallic bonding, less stronger metallic bonding. So, it will show lower melting point. Other than that, titanium, vanadium, and chromium order for the melting point is correct, which is increasing due to the presence of unpaired d electrons in them, or increasing number of unpaired d electrons, it is going to strengthen the metallic bond. Therefore, this given order is incorrect, because according to this order, the manganese is going to have highest melting point, which is incorrect. Now, for the D option, this order given is for increasing second ionization enthalpy, highest for chromium, then for manganese, then for vanadium, and then for titanium. The second ionization enthalpy, IE2, is the energy which is required to remove the second outermost electron from a unipositive ion. That means ion which is having a 1 positive charge. So it is already having 1 positive charge, then you are going to remove one more electron from it. The energy that you are going to need to do this is the second ionization enthalpy. Titanium configuration is argon 3d2 4s2, and the titanium +1 configuration is argon 3d2 4s1. Okay, here the first electron is removed from the 4s2 orbital, right? The ionization or the second ionization enthalpy for titanium, to form the titanium 2 positive, the second electron is removed from the 4s1 orbital, right? Because titanium positive has this configuration, outermost electron is present in 4s1. So, the electron removing is from 4s1. The second electron that you are going to remove is from the 4s1 orbital for the second ionization enthalpy of titanium. Now, it is relatively easy because the last electron is in the highest energy shell, the NS, that is 4s, and the resulting titanium 2 positive ion, which are going to form after the removal of second electron, has a 3d2 configuration, right? So, this is relatively easy. Okay, now let's see for another element, for the vanadium. So, for vanadium, the electronic configuration is argon 3d3 4s2. Vanadium positive has configuration argon 3d3 4s1. The first electron is removed from 4s2 orbital, right? Now, ionization enthalpy or second ionization enthalpy for the vanadium. For this, for the vanadium 2 positive, second ionization enthalpy means the second ion or second electron is going to remove from the outermost orbital, becoming or making the vanadium 2 positive. So, for vanadium 2 positive, second electron is going to remove from this 4s1 orbital. Across the period, you go from titanium to manganese, due to the effective nuclear charge increase, okay, there is an increase in the effective nuclear charge. It is generally harder to remove the electrons, which is resulting in a higher second ionization enthalpy for the vanadium compared to the titanium, because titanium was the first element in this titanium, vanadium, chromium, manganese series. Okay, and then vanadium comes at the second place. In the 3D series, it has some another place, but if you talk about these four elements, vanadium, titanium is the first one, then comes the vanadium. And because like effective nuclear charge is increasing across the period, when you move from the titanium to the manganese, it is going to be really harder to remove the outermost electrons. If you, and here you want to remove the second electron, this is also going to be like needed higher energy. So that's why the second ionization energy will be higher for the vanadium if you compare to the titanium. So the resulting vanadium 2 positive has a 3d3 configuration after the removal of second electron. Now, if we see for manganese having the configuration argon 3d5 4s2, the manganese positive has a configuration argon 3d5 4s1. The outermost electron is removed from the 4s orbital. So, the second ionization enthalpy for the manganese, if you talk about this, so it will going to form manganese 2 positive, and manganese 2 positive, in the manganese 2 positive, second electron is going to be removed from the 4s1 orbital, from which one electron is already removed, second electron is also going to remove from 4s1. Now it is resulting into the Mn2 positive ion formation, which has highly stable half filled 3d5 configuration. Mn2 positive has a 3d5 half filled stable configuration, right? And this stability of 3d5 configuration gained contributes to a higher than expected ionization, second ionization enthalpy for manganese, placing it higher than the vanadium. Okay, due to which this second ionization enthalpy is higher than the expected value for the manganese, and due to which this second ionization enthalpy for the manganese is higher than the vanadium. Now for the chromium, if you talk about having the configuration argon 3d5 4s1, so anomalous configuration, because it is going to gain stability from a half filled d subshell, right, after the one electron removal. So chromium positive, if you talk about having the configuration argon 3d5, and the single 4s electron is removed here, okay, from the 4s1. Now for the chromium second ionization enthalpy, for chromium 2 positive, second electron is going to remove from directly highly stable half filled 3d5 configuration, right? That's why we have written here that this is an anomalous configuration, because it is going to gain stability from half filled d subshell after one electron removal. Okay, so if for the removal of second electron, it is going to be removed from the d5 half filled stable configuration. Now this requires a significantly larger amount of energy due to the high exchange energy and the spherical symmetry associated with half filled subshell, which makes the second ionization energy of chromium exceptionally high. So the chromium will going to be more higher second ionization enthalpy, because the second electron removal is directly related to the removal of electron from the d5 half filled stable configuration. Therefore, this given order, which was highest for the chromium, then for manganese, and then for vanadium, and then for titanium, is the correct order. Thus, the C order, that is for this manganese, then chromium, then vanadium, and then titanium. For the increasing melting point was the only incorrect order we have found. Other than that, every order is the correct order. Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.